Hello everyone. Today's topic is graph coloring problem. The introduction to the graph coloring problem. The graph coloring problem assigns color to the vertices of a graph so that no two adjacent vertices share the same color. The objective is to use the minimum number of colors required to achieve this, which helps optimize resources in application like scheduling and network. And this is the problem statement. Input a graph G equal to P comma E, where V is the set of vertices and E is the set of edges. The output will be an assignment of colors of each vertex in V such that no two adjacent vertices have the same color. Goal is to minimize the number of colors used, referred to as the chromatic number. Chromatic number. What is chromatic number? The chromatic number of a graph is the smallest number of colors needed to color the graph so that no two adjacent vertices have the same color. There are some examples. A simple example could be a triangle graph where the chromatic number is 3 because each vertex is adjacent to other 2. In bipartite graph, the chromatic number is always 2 because the vertices can be divided into two sets with no edges within each set. Backtracking approach for graph coloring. Backtracking is a recursive technique that builds a solution incrementally, backtracking whenever a constraint is violated. For graph coloring, the approach tries to color each vertex one at a time. If a vertex cannot be colored with the current set of colors, it backtracks to try a different coloring. There is 5 steps. Start with first vertex and assign a color to it. Move to next vertex and try assigning the lowest possible color that is in conflict with its adjacent vertices. If all vertices are colored without conflict, the solution is found. If a vertex cannot be assigned a color, backtrack and try a different color for the previous vertex. Continue until all vertices are successfully colored or all options are exhausted. This is a pseudocode defining global variables. Colors should be arrays and graphs should be in 2D array to represent the graph, and B integer for number of vertices. Function is safe of vertex V, color C for each vertex I from 0 to V minus 1. If there is an edge between V and I and color I is equal to C, then return false. Not safe to color V with C. Return true, safe to color V with C. Function graph coloring util graph M colors vertex V. If V equal to V, return true. All vertices have been successfully colored. For each color C from 1 to M, if is safe of V, C, set colors of V is equal to C. Assign color C to vertex V. If graph coloring util graph, M, colors, V plus 1, return true. Solution found. Set colors of V equal to 0. Backtrack if coloring doesn't lead to a solution. Return false. No solution for vertex V with any color. Function graph coloring. Graph, M. Initialize colors array with 0 for all vertices If graph coloring util graph comma m comma colors comma 0 is false, print solution does not exist with m colors, return false. Or print solution exists with m colors for each vertex I from 0 to v minus 1. Print vertex I is equal to colors of I. Return true. The main function input numbers of vertex v and colors m, dynamically allocate memory for graph and colors array, initialize graph adjacency matrix with 0 for all edges, input number of edges for each edge, input vertices u and v, set graph of u minus 1, v minus 1 equal to 1 and graph of v minus 1, u minus 1 equal to 1. Since the graph is undirected, call graph coloring of graph comma m. The complexity analysis. Time complexity. The time complexity for backtracking solution to graph coloring problem is O big O of m power v, where m is the number of colors and v is the number of vertices. This exponential complexity makes it suitable only for smaller graphs, as it becomes insufficient for larger graphs. Space complexity. The space complexity is big O of v to store the colors assigned to each vertex. Applications of graph coloring. Scheduling. Assigning time slots to tasks or exams where overlapping tasks need different slots. Register allocation. Assigning limited time of registers to variables in a program. Map coloring. Coloring regions on a map where adjacent regions must have different colors. So this is the code for graph coloring problem. Let's run this program. So I have two graphs here, and one is with 5 vertex and 6 edges. So let's enter that one. We have 5 vertices and 3 colors and 6 edges. Now let's enter edges between 1, 2 and 2, 3 and 3, 4 and 1, 4 and 3, 5 and 4, 5. Now it shows the solution for it. The solution exists with 3 colors and it is 1, 2 and 1, 2, 2, 3. Let's check this example. Here we can see that red, we have assigned red, green, blue, and red, green, and red, and green, and blue. We are assigning this as the chromatic, which means we are getting the minimum number of colors used for this graph coloring. And let's see the next problem. Here we have for 4 vertices and 4 edges, and we have 3 colors. Let's see for that one. So 4 vertices and 3 colors and 4 edges. So that is 1 to 2, 2 to 3, and 3 to 4, and 4 to 4. these are the edges we have in the diagram also. So let's see. So the optimum coloring will be 1 2 and 1 2, which means this one we have vertex 1 2 3 4, and we have colors 1 2 1 2. From here we are going from first row, first graph, we are checking green or blue, and then we have red. And for green we can go this way also, and also this way also. We choose this one because this is the minimum number of colors we have used for the graph, so this will be the optimum solution for this graph. So that's all for graph coloring problem. Thank you for watching.